All right, we all see my screen, yeah? Cool. Okay, first thing I wanted to do is do a quick recap of what we did last time, and I actually realized that I need that CSV file because I always lose that CSV file. There we go. Okay. All right. So this is going to be the same data that we did with the last data group, the height and weight CSV. So import this stuff. This is height versus weight. And remember, we just did a regression and like got the best line that went through this. This was our summary. Just to reiterate, R squared is the amount of variance explained, the amount of variance in our weight that is explained by height. Some other things that I wanted to just say again are coefficient, very important to interpret. This coefficient of 5.539 means that with every 1 inch increase in height, there will be an increase in 5.539 pounds in weight. And that's just like generally how the relationship between weight and height. Saw some questions about p-values and confidence intervals. Just to reiterate, the null hypothesis that we are testing in every linear regression, same with multiple linear regression, we'll see later, is that the null hypothesis for each independent variable is that the coefficient is 0. So the null hypothesis is that this coefficient is actually equal to 0. And so this p-value of 0 means that we are very, very confident that this coefficient isn't 0. Again, I think Henry or Marv were talking about confidence intervals. And yeah, you can see that within these confidence intervals, 0 is not contained within them. So we are very, very certain with this case that the coefficient is not 0. Cool?
Real quick, Yish, I think I understand, but I just want to kind of just
for sure
iterate it. So the confidence interval of 4.9 to I think that says 6.1. That's the interval, but then the confidence in that interval is 95%.
Let's see. Yeah, because it's 0.25 and 0.975. So is that 95? I think it is.
Believe so.
Yeah, my brain it's been a long day, so but yeah, it is 95. Too, right? It is 95.
Yeah,
it is
sure.
95. Yeah.
So then I guess is the idea then that okay, we have a night where, because in like practical terms, like okay, well, I'm 95% confident that the coefficient falls between 4.9 and 6.1. Is that the correct way to talk about that, or no?
Technically, the correct way to interpret a confidence interval is that we are not super sure that this is for sure the correct coefficient. However, the confidence interval interpretation is that 95% of the confidence intervals that are generated will contain the actual true coefficient, which I understand is very, very abstract, but good news. I mean, also still very good to know, but in interpretation, we very rarely talk about like confidence intervals in this context.
So basically, so then that means that we're concluding that 0 is not the actual coefficient.
Yeah.
Right. Yeah. Because of the high, like because it's 95% and because it's at 95% confidence, it's between the ranges from 4.9 to 6.1.
Yep. Later on, we'll see some examples where the p-value is actually not 0, and then we can actually like maybe talk about it in that context and just to compare and contrast. But yes.
Okay. And they only rounded it to 0 because of 2 decimal points. Is that right?
Yeah. I'm pretty sure if we like extend the number of decimal points here, we will eventually see some number. But the idea of hypothesis testing is not to like confirm things, but it's more to like rule out things. So we've ruled out 0 as a coefficient, basically.
Gotcha. Okay.
Yeah.
Thank you.
Cool. You're welcome. That was just really good to clarify.
Sorry.
Yeah.
To go back to the coefficient,
Mhm.
how do we, I think you may have gone over this last time, how exactly do we
Okay.
interpret it when I'm blanking on what the word is, like normalized or standardized it?
That's a great question. So with a normalization or a standardization, you would actually have to reverse the coefficient. So we'll actually take a look at it a bit later, but not too in depth. But just because with like scaling, there is a library that we'll actually use in the next phase, but not in this phase. But anyways, for example, we log transform height. And we'll talk about transformations later, but let's say the log transformation of height is a better feature to use than regular height. Then you would say an increase of 1 in the log transform of height would lead to like a 5.539 increase in weight. Inversely, you can do a little bit of math and like reverse transform the coefficient as well to get that like direct relationship between the two, but it won't be linear. Like for example, like if it's a log transform, the relationship between height and weight would be more of like I think it would be like the e to the power or something. So it does get a little bit more complicated that way. If we scale our variables, we would have to unscale to be able to interpret it in context. But yeah, those are good things to keep in mind, that if you do any scaling, this relationship is with the scaled variable. So let's say, and we will talk about this later, I don't know if anyone has gotten to those sections, but there's many different kinds of scaling. For example, if we decide to min-max scale height, and min-max scaling usually like brings your variable, it just scales it such as between like 0 and 1 or something. And with that, you would then interpret the coefficient with that scaling in mind. And so you would have to know like how you scaled it. What did you divide it by? What did you minus? And I do have like all the formulas for the scaling below, so we can talk about that later as well. But yeah, you will have to interpret your coefficients with the scaling in mind. Anything else before we move on? Because I wanted to talk about making predictions, which we haven't really done yet. Cool. So we have this model here, and these are the coefficients that go into our linear model to predict. So for example, one thing that's a little bit annoying with stats models is a library, is there is code that exists that you can use to make predictions with like any number. So for example, if I want to give it like any height, it'll be able to tell me like what weight the model would predict, which is what we want our model to do. But unfortunately, stats models is not great with that. So I'll show a few examples, and we'll talk about what we can do to circumvent that. So let's take a look at our data frame again. Stats models predict function. So remember, we saved our model to the variable model. And how stats models works is it actually takes a row of your data frame to make a prediction. So if you have like a bunch of heights and weights and you just want to see how well your model does on specific data points, that's how it works. You probably will not be doing this, but I just wanted to demonstrate. So let's say I wanted to see what the prediction for this specific data point is. So I just used iLook to pull it out. This is a height of 71. The actual weight is 192, but what is the predicted weight? And how stats models does that? Stat models has a dot predict function that works on the model. And so you just feed it in that one row of the data frame. And you can see that this is the prediction of 188.78. And so what I had here is I feed it in like an index from 0 to 19 because that's our data set. But whatever that is, let's just print this out. I just wrote this little print statement to say, all right, this is the actual weight. This is the predicted weight. I should probably put the height somewhere. So let me just do that super quick so it's clearer. Let's add a print statement, height. And then let's do df iLook to predict height. Hope that works on first try. Perfect. So with a height of 71, the actual weight was 192, but the model predicted the weight to be about 189. So kind of close, but you know, you can, with like, if we're drawing a line through this scatter plot, different points will have a different amount of error. And we'll actually talk more about error in a little bit as well. But since we know how linear models, the linear regression equation is supposed to look like, we can actually build this predict function. Very easy because we only have one variable right now. But because we know the linear equation has the format of y equals to mx plus b, or in a different form, y equals to intercept term plus coefficient multiplied by the feature. So actually, let me just put this up. Let's see. Let's type it in this way. Y equals to intercept plus feature times, this is LaTeX language, if anyone's interested, multiplied by coefficient. It is not this way, it is this way. There we go. So this is the linear regression formula. Y is equal to the intercept plus feature times coefficient. If you have more features, it's actually plus feature 1 times coefficient 1 plus feature 2 coefficient 2, and so on and so forth. But because it's just one feature, we will just take W equals to intercept term, which was 204, plus 5.539, which was the coefficient here, multiplied by any height. So I just wrote this little function to, say it in a nice English sentence, that with a height of 60 inches, predicted weight of that many pounds. And with a height of, 70 inches, you'll have a predicted weight of 183 pounds. So this is a function that can basically make predictions for any height to predict any weight, to predict your weight with any height in inches. So based on this, do we really know how good this model is at predicting unseen heights and weights? Right? Not really, right? Because, well, this model was only built on 20 people. And I don't know what the actual relationship of weight and height is out there in the world. But if I were to randomly select 20 people, maybe from a specific country that has great water and people are just really tall and super skinny, I don't know, maybe there's a very different relationship compared to the rest of the world. And so because of that, we want to talk about, and we'll talk about this later, the idea of having a test set within your data such that you can validate your model that way. And that's something that I'll come back to here at the end, towards the end of this section. But before I get that, let's start talking about multiple regression. Any questions about this prediction stuff first? All right, cool. So multiple regression, let's bring back this data set which we've seen before when we were talking about NumPy and Pandas. We had this car data set, which I actually completely forgot is also in our curriculum. So good to see this back here. And so let's just fit a model on this data and see how it does. Let's not do any data cleaning. Let's not do any of these transformations that we need to do. Let's just see how it works. To set up a multiple regression, very, very similar to the simple linear regression. You can see here the formula has the same format. So in this case, we want to predict miles per gallon. And I'm pretty sure that's what MPG stands for. We're predicting miles per gallon. And it's going to be predicted by, so that tilde again. And in this case, because we have multiple features, we're just going to have every feature listed out, separated by plus signs. And that's the syntax of how you string all the independent variables together in this formula. Later we'll show if you have a bunch of features, how we can create this. But yeah, this I just manually typed in because it wasn't too many. So in this case, I didn't want.
So the tilde is used for mentioning that to predict things?
Yes. So the tilde sort of just separates your dependent and independent variables. So here, we're predicting miles per gallon with cylinders, displacement, acceleration, weight, year, and origin.
Okay.
Yeah.
And what is the easiest way to find out the dependent and the independent variables?
Well, based on your question, whatever you want to predict is your dependent variable. So for the project, you want to predict housing price. Housing price is your dependent variable. Everything else is independent. If you want to predict your income based on a bunch of other features, your income will be the dependent variable, like your, I don't know, age, level of education, everything else will be dependent variables. Independent variables.
Yeah, I mean, that's actually that solves the question, like whatever, right, I need to predict, I just put it as the dependent, and everything else I'll just put as independent.
Yep, that's right. Cool. All right, that was a good question to clarify as well. So this is just how you set up a multiple regression. Everything else is the same. You feed the OLS, the formula, and also the data frame that you're pulling from, called the .fit, and let's take a look at the model summary. So the model summary here looks very, 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 very similar. Here we have an R squared of 0.821. So that means 0.82 of the variance in miles per gallon can be explained by all of these features, which is pretty good, I think. Other things to note, we have p-values. This time we actually have p-values that are greater than 0. So we'll take a look at that in a little bit. But we also have coefficients that are positive and negative. So let's interpret some of these coefficients really quickly. Easy one, let's go with year. So basically, an increase in the year, so basically the 1 year newer the car is, miles per gallon goes up by 0.077. On the other hand, one more cylinder that you add, miles per gallon will go down by 0.41. So that's how you would interpret these coefficients. Pretty much in the exact same way you would with the simple regression. Now with
so in this, so for multiple one, basically is doing each, with the model is making each one individually and putting them on a line. It's like running multiple models and just start stacking them up like that.
Kind of. It's not really doing multiple, it's not doing multiple simple regressions because the features do have some effect on each other. Because so imagine, like, it's kind of hard to explain with more features, but imagine that I'm just doing it with 2 features. So if I have 2 features, I think it's best to explain with like a 3D graph. So I'm gonna just attempt to draw one. So let's see. Here, let's say we have like some 3D axis that looks like this. So imagine this is like 3D. This is like feature 1. This is feature 2. And this is our dependent variable. And basically our data points are scattered all throughout this area. Like they're all scattered around here, right? And so the line is affected by both x1 and x2. So you're not doing like, you know, just one line here and then one line here. It's sort of a combination of those. And so they're not particularly just running a bunch of simple linear regressions. It's just everything together. And like, if you have a feature with like a bunch of outliers, it will influence and pull the line in some direction. Does that help? Awesome.
So basically, Yish, would you say that, I mean, because I imagine this might be hard to explain, or maybe easy, I don't know, but the visual really helps me at least. Because I just feel like, okay, if you add another variable, you could, or yeah, another variable, the results, or the, I don't know what you refer to them as, but the results, they're going, they could be going in a particular direction, but it's not in this way that we see on a graph.
Yeah.
Right. Like when you add one, it is going in a particular direction. So it probably gets harder to do visualizations.
Oh yeah, you cannot visualize.
Yeah,
you can't visualize anything like past 2 other variables because we can't see.
It just gets crazy, right? Okay, yeah, I just wanted to make sure. Okay, but so when you did that, I kind of could see. Okay, well, it could be going in a particular direction. It's tough to draw it. But no, good job. Yes.
I'm glad. All right. So yeah.
So
Yeah.
now if we are going to run this formula, right?
Yes.
The model summary. Now within this model summary, right, how do we identify that which one we should use to run the linear regression? So like, let's say if this is covering all the columns of,
Mhm.
right? So, and in this, I have to select which one will be like the best one for the miles per gallon
Mhm.
and to run the regression. So I said,
Yes.
okay, now here it seems that the year of the car, right, has a better regression. And I'm just giving you an example.
Yeah.
Then on miles per gallon, than having the weight of the car or the origin of the car. So
Why? I'm just curious. Why do you say that?
I'm just wanting to select one of the factor, right, against miles per gallon,
Mhm.
for where I can say that because of this factor, right, the future, like, let's say if somebody has better cylinders, let's say,
Mhm.
right, it's possible that, right, their cars will sell better than, right, okay, somebody who has 4 cylinders, that cars will sell more in this year than the previous year or whatever, than the other factors. If I want to predict it that way, how do I identify with this?
Yeah, based on this output, like what features you're going to use. Yeah,
Yeah.
that's actually like a huge process of, that's actually a big part of the process of modeling, like deciding which features you're going to use. And through modeling, you actually do learn a lot about your features as well. So there are several methods to doing this. We'll be talking about feature selection when we talk about, well, I'm going to be talking about it now, talking about p-values after I explain what these p-values mean. But then again, when we talk about multi-collinearity of features. So first of all, when we're looking at these coefficients, a small coefficient doesn't mean that it's not a good feature. A small coefficient just means that, you know, every time you increase one in the independent variable, you just increase by a little bit in the independent variable. So a good example is, let's say this one, weight. The coefficient for weight is very, very small, right? It's negative 0.0069. So that means you increase, you increase weight by, like, I'm guessing it's pounds. You increase weight by 1 pound. It goes down by 0.0069. Miles per gallon goes down by so little. Yes, it's not a big change, but this is a very, very sure relationship because the p-value is 0. You're very, very confident that this relationship does exist. So as you can see here, p-value is 0. The confidence interval is like pretty small as well, negative 0.008 to 0.006. So this is well within that. And especially because the p-value is 0. On the other hand, with something like cylinders, and cylinders has a much higher coefficient in comparison, right? So we're saying that, like, you know, increase one cylinder, your miles per gallon goes down by negative 0.41. However, this p-value of 0.19, so almost 20%, is saying that there's a 20% chance that this relationship just happened by chance. So we cannot be very certain that this coefficient is not 0, is not actually 0. Right? So in this hypothesis testing case, it does get very confusing because the scale of your coefficients can be very, very small. But a small coefficient with a low p-value is still a very certain relationship. Rather than having, you know, a larger coefficient but a larger p-value, you're maybe not so sure of that relationship. And that's why I think, like, you not only have to look at coefficients to be able to, like, you know, connect your independent, and your dependent and independent variables, but you also have to take a look at p-values, because p-values tell you, like, what is the probability that this just, you know, happened by chance. And that's why we have to talk about hypothesis testing. So as you can see, this is 0.191. And it is very, very close to the boundary of actually like it's within these confidence intervals of like 0.210. So that means in that region of like 0.1049, negative 0.1049 and 0.210, within that region, you actually do not reject your null hypothesis. So you're, in this case, if your alpha is at 0.05, you're actually failing to reject your null hypothesis, and you cannot say that this coefficient is not 0. Does that make sense? Nah, I see a head shake. Basically, with this large p-value, you have a 20% chance that this coefficient might act. There's a 20% chance that this coefficient of negative 0.4198 happened by chance. So you cannot say for certain that this coefficient isn't actually supposed to be 0. So because of that, usually what you would do, one of the ways of feature selection is you would take out features that have a high p-value, because they're not very certain that there will be a relationship between cylinders and miles per gallon. I mean, I don't know too much about cars, but does cylinders and miles per gallon are they usually related? I don't know.
So basically what you're saying is that, so this is like one of the first steps when you're looking at when you're looking at this, least squares, is you take out the one that has the highest p-value to see if it'll erase the r squared.
That's right.
Gotcha, okay.
So what do those two columns mean after the p-value with a 0.25 and a 0.975 again?
This is the confidence interval. So basically it's like the value that's at like 0.025 and the value at 0.975. It's basically your 95% confidence interval, and the values.
Like if you're looking at a bell curve, if you're looking at the histogram, whatever, or distribution.
That's right.
Like a two-tail?
Yeah, it is a two-tailed. Yeah.
Okay.
Yeah.
Okay.
Yeah.
So you're saying that the p-value for the cylinders is very close to the right end of that.
Yeah, and it's actually within that as well. Let me see if I can like draw it on a board real quick. So
It's within it.
yeah, it's within it, which is not what we want.
But it looks like it's right to the left of it. Because if you're looking at like a number line, it would be to the left of 0.210.
Yeah. Yep. So let's see. With these values, this is our curve. I'll show you all the curve. I just need to like write these numbers out first. 0.21, and then this is negative 1.049. So with those values, this is what our curve looks like. And this in the middle is 95%. Yeah. So this middle part is 95%. This middle part, if your value is in the middle, coefficient equals to 0. In the middle part, if your value lies between these values, it's saying that your coefficient is equal to 0. And it so happens that that coefficient of, sorry, not that coefficient, but that, oh my gosh, I totally said that wrong. Wait, let me double check real quick. I think what I meant to say is, so let me rephrase everything I've just said. The p-value is the area under the curve, right? It represents the area under the curve at a certain point. So what that is, I was incorrect in saying that like that point, that p point was in between that, because that's totally not what it is. So that is 100%, that was wrong. That p-value is saying that it occupies 20% of like an area of 0.191 under the curve. That is the correct interpretation of that p-value, which is too much, because in order for you to reject that null hypothesis, it has to take up like these amounts, which is 5%. Yeah.
Okay, I think I'm getting it.
Yeah, yeah. I'm so sorry about that. I like got super confused with like the t statistics and that.
That's how it makes sense. Like when we are rejecting any kind of hypothesis like p-value, if it is more than 5%, right, that prediction is as good as like your hitting something like vague.
Yeah, and I was actually reminded about that because I looked at the T statistic, which I haven't been really talking about, because usually the T statistic is basically like the number when you convert it to the T distribution. But basically, this T statistic of like negative 0.311, yeah, I don't know. Wait, let me like rethink this a little bit more. Usually if your T statistic is smaller, like the absolute, if the absolute value of your T statistic is smaller, it falls within your confidence interval. If we remember our T distributions. If your T statistic is smaller, that's like the deviation away from the mean, right? So if a T statistic is smaller, it means that it's probably within your confidence interval. Because your confidence interval is some interval, and if your curve is like this, if your T statistic is small, means your point is not that far away. So that's why with these bigger T statistics, the bigger absolute value of T statistics, your p-value is lower. That is the connection between p-value and T statistic. Yeah, that was super confusing. So that is on me, but please ask clarifying questions whenever needed. We might run long on this because there's still a lot to go through, but good news is section 20 is shorter. So if anything we don't end up covering, I can cover in the next study group. But cool, but this is just like the first pass of our multiple regression.
Yes, one thing I'll say is it would be nice if you did some visuals for some of those variables. Just so I know it'd be good for me to just see, okay, you know, this p-value is saying this, and so this is the interval range or whatever. So not now, but I mean, at some point, I think it'd be great.
Yeah, absolutely. I'm gonna look some stuff up.
All right, thank you.
Yeah, that's actually really good to know that visuals will help. But cool, yeah, this is basically our first pass of a multiple linear regression. And with this first pass, what we've garnered is that, you know, these like maybe cylinder and possibly acceleration, because it is a little bit higher, might not be as reliable independent variables to predict miles per gallon. And so usually after you run your first like full multiple linear regression, that would be like a first step of feature selection to just take out high p-values. But cool. Does anyone see any problems with like, you know, the features that I'm running? I guess a hint is the next section we're going to talk about categorical variables. Cool, that's fine. Basically, some of these features might be better represented as categorical variables. And categorical variables is not something we've really talked about yet. And in this scenario, especially in this scenario, it's a little less obvious because all of these columns are all still numerical. Something to talk about with like, you know, numerical things that could be categorical is you do have to have a little bit of contextual knowledge. So I don't know too much about cars, but is it always the case that the more cylinders you have, the higher your miles per gallon? So I don't know too much about that. We're gonna plot some graphs to look and see if that's the case. But cylinders is one thing. I don't even know what origin is in a car. With years, does miles per gallon get higher every year? I'm not too sure about that. But with contextual knowledge, whether you decide to turn something into a categorical variable or not does depend on whether you're sure that there is that like linear positive or not positive, or if there's like a constant relationship. Is it that like, you know, if cylinders go up, miles per gallon is sure to go up. If that's the case, sure, you can keep it as a continuous variable. If like different amount of cylinders doesn't necessarily lead to miles per gallon increasing, turn it into a categorical variable, because 4 cylinders could be a completely different category from like 8 cylinders. But anyways, to talk about categorical variables, there's a lot of code here and I'm just gonna talk through each one. So the ones that I sort of can see are more, what was I gonna say? I'm basically going to plot scatter plots for all the variables. So here we have acceleration, displacement, horsepower, weight. For these, you can sort of see, all right, there is some linear relationship between these three. And interestingly, with acceleration had a slightly higher p-value of like 0.41 compared to, if we compare it to displacement, horsepower, and weight. Displacement was here, 0.1 p-value. Horsepower, I guess I didn't even put horsepower in this, but weight was 0 as well. So you can sort of see that there's some relationship there. If this doesn't look as linear, your p-value is not going to be as small because it doesn't seem to be that higher acceleration. It doesn't seem to be that there is some linear relationship between miles per gallon and acceleration. These, after plotting scatter plots, look like ones that could possibly be categorical. So let me zoom in a little bit on this one a little bit. So because there are quite a few points, I did like the alpha so that you can sort of see a bit of the density of the points. For cylinders, you can sort of see that it might be a linear relationship, right? Like you can kind of maybe draw a line through this like this possibly, or like something like that. So there might be some linear relationship, but of course we have these points down here. Let me undo that. We see that there are these points down here that don't really follow that relationship. What are these points here? What are these points here? The more contextual knowledge that you have with your project, the more informed your decision will be. But I'm going to treat this as a categorical variable because I don't know too much. And yeah. Similar with these other variables. With year, it seems to be like the densest part of each year is like kind of up and down, right? Like this seems to be the densest here. I don't know about this, but this is down here. This seems to be like in these areas, down here, maybe up here. So even though overall it kind of looks like there is some like upward trend, if we're looking at the densest points of each vertical line, you can see that we can't really tell what kind of relationship there is going on. And same with origin.
Could you define categorical variable?
Yeah, categorical variable, kind of as the name suggests, is categories. And so what we're going to end up doing is we're going to end up having columns that actually it'll make a little bit more sense once I run the next cell. But let me actually do that first. So categorical variables are also known as dummy variables. And a categorical variable or a dummy variable is a variable that takes a value of 0 or 1, depending on whether that row has it or doesn't have it. So in that case, what we're going to do is, because for cylinders, let's see, there's 3, 4, 5, 6, and 8. For cylinders, and let me just like run this really quick. There is a built-in pandas function called getDummies that turns it into categorical variables. So let's actually take a look at what cylinder dummies looks like. If you can see here, it basically will turn each cylinder, it'll turn the cylinder column into 4 different columns. So I guess there's no 3 in this data set. So it's just 4, 5, 6, and 8. And basically for each car, it'll be a 1 if it's, for this case, it's an 8-cylinder car. So it's just 1 in this column and 0 for all the other columns. So that's what these 4 are categorical variables.
Now, quick question. is that kind of, is this normal or is it kind of soon to turn it into a dummy variable?
So that turning things into dummy variables should actually be a step that you do before you even run your first model, because you should have an idea of what your features are. And if your features are in categories, you should turn them into dummy variables before you put them into the model. So actually, if we take a look right now, these categorical variables like year, let's take a look at year. I think I have year in there, but year does not have much of a relationship with miles per gallon. But, and oh yeah, and if we look into here, oh, it actually does have a p-value of 0. It could be all the features working together, but ideally year is something we want to take out, and we'll actually run this model again with the dummy variables, and you'll see that the model, I think, does a little bit better. But this also doesn't really make sense, right? Like if you increase your year by 1, having your miles per gallon go up by 0.77, I mean, I don't really
Well, I think it does make sense in a way, because you could say that cars will get more fuel efficient as time goes by and they get better technology.
For sure, yeah. And if you believe that that's the case, and I don't know what the case is, you can keep it as a continuous variable for sure. I just like, based on me not knowing anything about cars and looking at this scatter plot, I couldn't really say. But something to keep in mind is that people work on like single regression models for like months, and we only have like 2 weeks to do it. So unfortunately, we have to like, you know, make decisions on like what are the things that we should be doing now and should not be doing now. But yeah, that's a really good point. I don't know what I guess miles per gallon means like the miles that you can go on 1 gallon of fuel. So that makes sense that you get more efficient. I'm only just realizing this now.
Just a quick question, like
Yeah.
on the year, why it is like it's mentioned in points, not in the actual year?
This is just the way the data set was, I think. Yeah, like why is it like 70, 72, 75?
Yeah, 72.5, not even 72.
Yeah, I think this is just like the automatic way that it was rendered on this graph, because the where the points are actually like 70, 71, 72, 73. So none of the points are actually on the 0.5.
Mhm.
Yeah, but I think that's just like the matplotlib and how it automatically generated. But cool. I want to at least get to talking about multicollinearity. So anyways, with categories, and it'll actually be more obvious in other data sets where maybe if you have like car color and they have like the different colors, you might want to have a dummy variable for each color. But cool. So this code basically turned cylinder, year, and origin into dummy variables. What this does is, let me just explain this method. It takes in the column that you want to turn into dummy variables. You give it a prefix just so like it automatically creates these column names of like cylinder and then whatever value was in that column. And then drop first equals to true actually ties into the multicollinearity thing. There's a really good write-up on it in one of the labs, but it's what's called the dummy variable trap. And basically, you always have to drop one of your dummy variables because, oh yeah, that's where the 3 went. You always have to drop one of your dummy variables because if you don't, there will be perfect multicollinearity with your variables. I can definitely talk about that more maybe in this next section. But what I wanted to show really quick is that now we've dropped the original columns, concatenated the dummy variable columns. Now our data looks a bit like this. For this part, these are the columns that we're going to use. The first one was miles per gallon. And this is just so that I can join it to make that formula. So this is just string concatenation. I had the miles per gallon tilde part. And then this is a dot join method that I'm just joining all of these individual strings with a plus sign. And then I have my formula automatically generated like this, rather than having to type each one up individually. And really quick, run this model. And you can see that, well, one, there's a bunch more features, but I think our R-squared does go up. So let's take a look at what our R-squared was before. It was 0.21. And then now our R-squared is at 0.87, adjusted 0.86. We have more features, so more things to look at. But yeah. Any questions so far with like this stuff? As you can see here, there's going to be a lot more feature selection to be done. This technically should have been the first model that we ran because a lot of these maybe should have been turned into categorical features first. And then from here, you can see that there are a lot of them that have high p-values. So for example, acceleration, which I think we kind of saw with here, very high p-value of 0.967. That we definitely might want to take out. Things like a car being made in the year 71 or 72 or 73. And so all of these are features that you want to take out using the p-value elimination method. Questions on that?
So how do we just drop the rows and just say like anything with, like, let's say if we have write a function which says that any p-value which is beyond is 0.5,
Mhm.
0.05, right? Just drop it. Something like that. Can it be done?
Kind of, in a way, sort of. So for example, this model.summary, I think you can index this. Oh, no, you can't index this. Since you can't index this, you probably end up doing it literally by like doing it manually. There is another library that I'm actually gonna show at the end, scikit-learn. I don't know if we'll make it today, but scikit-learn is a little bit easier to do this. Just because it's in like actual like list formats that you can, you know, zip and then remove. But that was just like an overview of like categorical variables. And typically you would do that before you even run your first model, since, you know, you should have an idea at least of what is categorical and what isn't. Any questions on categorical variables?
So once we run the dummy model, we just need to write concat all the, or join maybe all the columns, and then make a data frame of it, and then run the other modeling part, correct?
Yeah, yeah. So let's actually let's like really quickly try this out. Let's see, where is this? Let's see. This is our original formula, and let's do this. F equals to this, and let's take out acceleration. Let's also take out, let's see, let's take out years 71 through 73. So years 71, 2, and 3, let's just take that out. And then with F as that, let's rerun our model and see what happens. We rerun our model, and our formula here is F, same data. Let's take a look. By taking out those features, I think our R squared does go up or down a little bit. Very, very similar, goes down, but we should actually be looking at adjusted R squared. Turns out not a big difference. But in this model, we're not using features that have high p-values. And actually, by taking out those features, because all of the features are related to each other, previously, we had a bunch of other features that had really high p-values that we didn't really take out, right? Like year 74, 75, and 76 technically also were above 0.5. But by taking those out, by taking those others out, well, I guess these are still high, but the p-values overall have gone down a little bit because everything kind of works together with each other. But anyways, this is going to be an iterative process. Usually you would set some sort of, you will have a threshold of 0.05, and none of your p-values should have a value above 0.05. All right, I want to move on really quickly to multicollinearity of features. So the idea of multicollinearity of features comes from the idea of redundancy. So imagine, let's say in this data set that, let's actually take a look. I did a data.core to see which features are very correlated with each other. So let's take a quick look. Something that's very correlated with each other, horsepower and displacement are very correlated with each other. So that means that if we were to take the plot of horsepower with miles per gallon and displacement with miles per gallon, they should look quite similar. And I actually think we might have that here, right? Horsepower and displacement, these graphs actually look quite similar, right? The relationship is very similar. And so the idea of multicollinearity is that why use more features when you don't really have to? Since they have very similar relationships to each other and therefore with miles per gallon, for redundancy's sake, we shouldn't use both of them as predictors. And so therefore, if things are very correlated with each other, we want to take those out.
Couldn't you also say that miles per gallon and weight are similar to horsepower and all that?
Yeah, for sure. I think if we take a look at the correlation with weight, it'll tell us that, yeah, displacement and weight is also really, really high. So like these three, displacement, horsepower, and weight, are very correlated with each other. And I think if we take a look at, yeah, displacement, horsepower, weight, all of these values in this like square are very high. So in that case, you might end up taking out 2 out of 3 because having one of these features is good enough and pretty much has the same effect. Does that make sense? It's a little bit abstract in the sense, but I sort of like to think of it as like redundancy. And also something that does come up is what this is not as important, but multicollinearity is an issue. And you can see that this warning came up and tells us that we don't want that multicollinearity there. And so some processes of doing that. One thing you might want to do first, remember our from Monday's study group, we talked about the linearity of features with your target. So if we actually take a look at the correlation between miles per gallon and all of our features, this is a very crude way of doing it, but I just wanted to cut down the features so it's easier to talk about things. You should be doing this more with like scatter plots or something more visual because, anyways, I just set some boundary of 0.03 to just basically reduce the number of features that I was dealing with for the purpose of this lesson. And for this, because this only lowered the number of rows, let me just get rid of it in the columns as well. Now I just have these features here. So now it's easier to talk about some specific ones. And so the ones that are highly correlated, I think we had talked about weight and horsepower and displacement. In this example here, yeah, I actually ended up dropping weight, displacement, and cylinder 4, because cylinder 4 also had a lot of things that were correlated with it. So you can see here a lot of numbers like 0.75, negative 0.82, a lot of big numbers here. So because cylinder 4 happens to be correlated with a lot of other features, I wanted to drop that as well. And so through dropping that and dropping this as well, and I guess I ended up dropping cylinder 8, we can rerun our model and see what happens. So with our model here, you can see from dropping the multicollinear features, we have like a good number, pretty much all our features, yeah, all of our features are at a p-value of 0. R-squared goes down, but that's kind of what the adjusted R-squared is for, because the R-squared always goes up as you add features, and that is more about like number of dimensions that you have. But just good to know that multicollinearity is something that you have to look out for. Questions? These are like a lot of little parts of the modeling process. But yeah, multicollinearity might be something that you do perhaps after running your very first model. Maybe you take out high p-values, and maybe also taking out the collinear features might help with the p-values too. It is a very iterative process. There's no like do this first, then do this, but yeah, those are the things. Let's see how much time we have. We are pretty close to the end. I think I'm going to talk about transforming features the next time. But before that, I think something that we can talk about in this time is model validation, because I did start talking about that before when we were making predictions. This is all copy pasted from the lab, but I just wanted to talk about why we need to do this thing called a train test split. For every single model that we will be running in this course, we'll be doing train test split. And train test split basically helps us to understand whether our model is good at predicting on unseen data. Basically, there are these ideas of underfitting and overfitting. This is not like particularly for the case of the linear model, but if these are your values, this is a model that's underfit, right? If this is the model that you end up choosing, if you predict something on the low end, if this is what your actual model looks like, and you decide with this to go with this model, points that are up here are going to be with high errors. Maybe points that are down here are also going to have high errors. You always want to have a good balance between over and underfitting. something like this, which is like in the middle of these three diagrams, is a pretty decent balance compared to this overfitted diagram where you have, you know, this line going through almost every single point. Downside of this is if you had unseen data, like let's say like up here, one, how is this line supposed to look like on the to the right of what this time graph is? But also, what about points that are like here? If a particular point is, let me just draw this super quickly. If a particular point is here, and your model line is down here, you're gonna have a huge error. But a point in this area technically shouldn't have that big of an error. So there's this whole idea of over and under fitting, and also being able to see how well your model tests on unseen data. And that's why we have to do a train test split, because a train test split allows you to take some of your data, put it aside to use it to test how well your model is doing. That's kind of the last thing I wanted to end off with, just like understanding what a train test split is. There is some code down here doing a train test split, but I'm gonna leave that till next time to talk about. Any overall questions? Cool. I know we covered a lot of like random things here and there today, but feel free to let me know if you have anything that you need to clarify. But yeah, I know some of you have started looking at the project. Highly recommend that you do so. You don't even have to start doing it. I think it's a really good idea to at least look at what the project is about. But yeah, that'll really set you up for success, because we're only going to introduce it. We are going to introduce it next Thursday. Cool. Awesome. In that case, we're a little bit over time. Have a good night, everybody. And as usual, any questions, just let me know. All right. Bye, everybody.